There we go. Almost perfect. Ooh, I lost the connection. All right, ready to go? Double check. Any of you has been working with a simulator a little bit more? Any success stories? Hey, that means everybody is successful. Should by now be close to bug free, besides what's happening on your personal computers or the computer you're using. We will need that, so I'll try to get the homework out for you today, and you will need that simulator to do something. Cool. Today, one more topic. Again, we are kind of past the point where we did the kind of main basic material of robotics. And now come tidbits. The last time tidbit was optimal control. Just to give you a feel for how it's formulated, is that a cost function? You sum up costs over a time horizon. You may have terminal cost. And then you basically try to optimize that cost with respect to the motor command along this time horizon. And that can become pretty complicated in arbitrary nonlinear systems, but in linear systems, it became simple and became LQR control. So linear quadratic regulator. Linear because the system was linear, we assumed. Quadratic because the cost function was quadratic. And regulator because you usually try to get the system to a particular set point at which you want to operate. So that was LQR. Now, interesting is that there is a equivalent development which is in state estimation, and that is called KalmanFiltering. And for linear system, linear quadratic regulator control and KalmanFiltering become almost identical. You will see the update equations are essentially identical, just that you arrive in a slightly different way. So I want to talk a little bit about KalmanFiltering today. It's a very important framework which people use a lot. And it's good that you at least know a little bit about this. Again, it's another tidbit, optimal control, KalmanFiltering. We also do force control at some point. And maybe we do a few more of those things, but it will mostly become now project-oriented afterwards. So let's get going on that. Let's see. OK, so this is really what I want to consider. And this is a block diagram which you have seen before, just slightly differently formulated this time. OK, the red thing, or pink, or whatever it is the robot. And in the robot, there is kind of a system which kind of changes its state. That's kind of the dynamics of the system. And there's a measuring device which gives you some feedback what the system is doing, for instance, position sensors on your degrees of freedom. OK. Now, you have the ability to send in controls, and you have the ability to read measurements out of this thing. That's really what you can do. Practically, we know that there's a system state in there. There's our little X or Q or whatever you want to call it. But really, we don't know it until we get some measurement from it. And what we have to assume is that the system has potentially some error sources. Particularly if we model it, it may have some error sources, but maybe stochastic by itself. And the measuring device may also be contaminated by some error sources, like just noise. Okay, so you get actually some contaminated stuff out of there. And then you want to put in a filter which basically gives you as good as possible an estimate of the system state, of the entire system state. You actually observe measurements maybe too few. So for instance, again, we have on a robot typically position sensors, but we don't have velocity sensors on them. If you want the state of a second-order system, you need position and velocities. That's the complete state. So we need to somehow figure these out and uncover that. So let's look a little bit in the basic setup of KalmanFiltering, and then a little bit about the derivation of it. The derivation is, again, lots of matrix equations. You will not like them too much, but it's good. I just want you to see these things once, that they don't look like they're just voodoo or complicated weird nonsense. even if you don't feel it beautiful when you will see some of the slides are disgusting. Fine. When do we want to use a Kalman filter in general? We want to eliminate noise in our measurements. That's a very common thing. We can also do this in different ways. We can do this with this digital filtering, like Butterworth filtering and whatsoever, and we'll talk about this a little bit later. But Kalman filtering is a more powerful way of doing it. We want to generate non-observable states, for instance, again, velocities from position signals. So that is actually something people like to do a lot. And a more complicated example of that is actually if you have a normal humanoid robot, for instance. So here I get my little stick figure. And the robot has something which we call the base coordinate system, which usually is the pelvis, but totally arbitrary. You can make it your nose if you'd like to. And in there is usually an IMU. Okay, IMU, inertial measurement device. These things measure usually linear accelerations and angular velocities. That means how quickly is something rotating and how quickly is it translating, including what our good old friend gravity is doing, who's pulling us down all the time. Now, so what you get out of here essentially is some acceleration that would be x double dot and some omegas that would be angular velocities. Now you have to use this stuff to actually figure out where is that base. Since it's not measured, we cannot put a position sensor on this robot which measures absolutely where it is and how it's oriented in space. So we would like to know x and usually a quaternion q for the orientation. So this is a quaternion. Did I get a telephone call? Is that true? Okay, yeah, that's irrelevant. Sorry for that. No, I lost my marker. Cool. So this is a typical state estimation problem where you get some signals which are not directly what you want. And out of those, you have to create these correct signals. And that's actually non-trivial in this particular case. Because you can already imagine just from knowing how fast you move or how fast you're rotating, or you cannot figure out where you are properly. And actually figuring out what's the orientation of your body is not that trivial either. So this is a more advanced example of Kalman filtering where you uncover unknown states from some measurements. And this is still research, so people working on that. I have people in my lab who work on that. At other universities, people work on that. People basically work on that in complicated systems. Good. So this is where generate non-observable states come from. Generating velocities from positions is a very trivial example. Most of the time, we wouldn't do it with a Kalman filter necessarily. We can do it by simple differentiation and filtering. We also care about prediction of future states. You will actually see that in a little bit how the problem is formulated. It means if you have a system which has significant delays, you can try to predict out the delays if you have a model of the delays. That means I'm here, get some measurement, but I really know that I'm some delta t in the future already. And with the help of the Kalman filter, you can actually do that. And in the end, Kalman filtering does something which is called optimal filtering. Rule number one in life. Someone tells you optimal. First question you ask, optimal with respect to what? There is no optimality, so to speak. It's optimal with respect to a particular cost function. This is a statistical cost in this case. It is basically optimizing the prediction error of the Kalman filter. So you will see a little bit more about that as well. Okay, so this is kind of the setup. This is what we can do with it. And you will see in a moment, and I'll put this on slides again, it requires a model. Without the model, Kalman filter doesn't work. But because it has a model, and if the model is a good model, you can do better filtering than you could just do with digital filters, which, you know, you can think of a simple digital filter. It's like, I showed you this long time ago when we did Laplace transforms. If you do something x dot equals alpha times, let's take this and call this a measurement here, let's call it y minus x. So y is now a noisy measurement of x. Well, if I put y in here and let it run and develop, then x becomes a filtered version of y. It's a crummy filter, but it works. The same idea you can do and create more complicated filters, and I'll talk about this with polynomials, which have much better properties. But it's the same idea. You basically use some kind of knowledge, some kind of smoothing, which delays your system a little bit, but then you get rid of the high-frequency spikes in your data, which you assume is noise. Just you can do this in a more principled way with proper digital filtering. But using a model is a much better way of doing it, since you can actually predict things based on the model, and that's where you don't get as much delays, for instance. Cool. Here we go. The Kalman filter was kind of invented in 1960 by, guess who, Mr. Kalman. He actually gave a talk here a couple of years ago at USC. He's still happily alive. Most likely heavily quoted. We need the basic setup to get going with Kalman filtering. And we take this again into a discrete time domain because it's nicer, and you will see very soon the connection to LQR control. And we take it into a linear domain, since that way it was developed. And we can talk about the nonlinear extension in a similar way as we talked about the nonlinear extension in LQR control. Becomes essentially local linearizations at a certain point and applying then the normal standard linear approach. Cool. So fine, system equations. So this is the model, very important. We do have a model. Again, the same system as we had the last time. Now one new component. We assume there is a noise term Wn. Okay? This models that we don't know our model. It's kind of annoying. So it's a very simple fudge term which says this model may not be entirely accurate, thus I allow a little bit of noise which jiggles me back and forth. It's a very cheap way of modeling if you don't know what to model. It's really annoying. You can also, so what people, for instance, do, if you have a constant state, people create actually state equations which say yn plus 1 equals yn plus wn. So this is now a drifting system. Normally you would assume yn and yn plus 1 are completely constant. But maybe it's changing due to some reasons over time. So if you add a noise term here, it becomes a drifting system, which just wiggles slowly away. Very cheap way of modeling. It's not a good model, okay? It's a pretty shitty model. It basically says, I have no clue what I'm doing, so I just add some arbitrary noise term. The other thing we have is our observation function or measurement function. And that is yn equals c times xn plus vn. So that just means that the true state x is somehow transformed by the matrix C to give me the observable y. Okay? And again, there might be some noise term which gets injected, since I may have measurement noise. Okay, super simple example. If I wanted to just create, if I have a proper state which consists of position and velocity, so this is my proper state of a second order system, well, I can create a observable position state only by this matrix C. So that would be quote unquote y. That would be also equivalent to x. So I can only observe x. This is what this equation says, nothing else but that. Okay? Now you can imagine how you can basically put things together. You could also put in differentiators in the observation equations and all kinds of stuff. Good. Some knowledge. All of you know expectation operators. You're great statisticians, aren't you? No. Okay, fine. Expectations. What is the expectations of a noisy variable? Fine, let's take a little noisy variable, usually called epsilon. And you observe an epsilon at time step 1, epsilon at time step 2, epsilon time step 3, blah, 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 blah. Okay, now let's assume this is all the same value, just noise contaminated. So our model would be that what we really see here is essentially some true epsilon plus some noise term, call it some eta or something like that. Okay, this is my observed epsilon. Let's make this here true. I don't know how to make it true. Make a underbar or whatever. Okay, So it's just a noisy process. There's a true epsilon, and then someone adds always noise to it. So how do I find out the expectation? Well, the expectation in all other cases is simply the mean. And the mean is then trivially the sum of all epsilon I divided by the number of them guys I have. So I goes from 1 till n. So that is, in this case, the expectation of epsilon. Okay? Just the mean operator. If you want to go into proper statistics, then the mean in general is this. So the mean is defined as the integral of the probability of a variable times the variable integrated over the variable, over the domain of the variable. That's the real proper definition of it. In our case, what we did, we assumed that each data point has the same probability. The probability was 1 over n for every data point, which is a uniform distribution. And then we just had the epsilon values, summed them up, and you converted the integral and just sum. That's it. Okay, now, so then this notation simply means that the mean of our noise is 0, which is a generic assumption which everybody makes. If the mean of your noise is not 0, then you have an offset which you don't know about, which is highly annoying. The mean of the other noise variable is 0 as well. Then the covariance, remember, variance is something like if you have the mean of a variable and the variable, then you simply take the difference and square it. Again, you sum that up over many data points, I equals 1 till n, and divided by n. Okay, that's a variance for a univariate variable. For a multidimensional system, it becomes a matrix. And you take the outer product, so that means W times W transpose gives you the covariance matrix. That's called Q, and here the covariance matrix is called R. And then there's a cross term which simply says W and V are not correlated. The noise is completely independent. Okay, that's all what that says. So this is just, yes.
Is W and V have the same dimension?
They're just noise variables. Dimensions, they are basically the appropriate dimensions in that particular equation. They're just noise in those, how they're scaled and what they mean is different.
Yeah.
So here, basically, well, in this case, actually, this, well, Y, I don't know what measurement we have, and X, I don't know what measurement we have. But all what we care about is what is the statistical properties. We don't care about the scale. The scale is basically in R and Q. It's absorbed there. The dimensions don't really matter in this case.
But if they don't have the same dimension, how can they do a cross product?
Oh, fine. Oh, now I understand what you mean with dimension. Okay. Yes, in this particular case, well, let me see. I can do an outer product with any two vectors, can't I? Let me see. Let's do x1, x2. Outer product of it with y1, y2, y3. That would always work, doesn't it?
Oh, yes.
Good. So we don't need different. We can have different dimensions. It's just not a square matrix anymore. What comes out of it? But all we care about is 0. It means the noise, if X is a noisy variable, Y is a noisy variable, the two of them are on average uncorrelated. And that's important. Because correlated noise creates a lot of misery as well. Okay, so, and we want to basically, based on that, because we only observe Y, we want to get the best, in the end, recursive estimate of the state X of the system. So this is the setup which we try to accomplish. Some derivations make actually assumptions about what kind of noise you have here, whether it's Gaussian noise or non-Gaussian noise, for instance. I think in the basic derivation you can avoid that. You just need to know that there's a mean 0 noise process on it. Okay, so one more time summarizing. This will allow us to estimate past, present, and future states. So where does this come from? Well, the future I can predict with the help of those equations. That's just a model. And if I would apply it multiple times, I can predict actually far in the future, just my kind of confidence in this will go down. We need a model of the system, which we just saw. And it has to be good enough, approximate works, but then you inflate most likely that W term. You will figure out that these two noise terms become a little bit twiddling parameters. There's some truth to them, and then people tweak them until they get the performance they want. This is better than digital filters because we use models, and we need much more knowledge, structural knowledge about what we're doing. The Kalman filter is optimal for linear systems. There's extensions to nonlinear systems where we just basically do local linearizations, apply the same equations again. This is called the extended Kalman filter. There is a small note on that. Because we assume that we are pushing noise processes through equations, here's kind of one of the annoying parts of life. Running a noise process through a nonlinear function is potentially problematic. This is actually worthwhile noting once in your life. So let me do something hopefully useful. Let's assume we have a variable epsilon again. This is the probability of epsilon. Okay, let's do something really lovely. We assume it has a Gaussian distribution. Remember, Gaussian distributions means the mean 0. So this here is the mean, in this case, and it's 0. The distribution looks like this. It's a typical probability distribution, a Gaussian distribution, which is used a lot in statistics because it automatically happens if you have many noise processes mixing, you get Gaussian distributions. There's a good justification for that. So this is fine. The interesting question is, and the mean here is well defined, it's just in the middle. If we do a sine function of epsilon, okay? And now we look at the probability of this nonlinear transformed thing. How would that look like? The interesting part of this is that P of sine of epsilon versus epsilon will suddenly, now I have to get this right, the sine goes from 0 to 1, so here's -1, here's 1. We'll get a distribution which will look something like this out of that. So why is that the case? Well, look at the sine function actually over time. Sine function looks like this over time. So now this is time, that would be epsilon. Okay? Now basically what we're looking at is how often is the particular epsilon here, well this goes from 1 to -1, how often is an epsilon up there, how often is an epsilon down there, how often is an epsilon there. It turns out you have many more data points in those areas than in this middle area, where you actually pass through really fast. That basically creates that bizarre distribution that you have more stuff here than there. Now, the interesting part of this is now called a bimodal distribution. Again, you take the mean of that. The mean is smacking in the middle. But that is a very unlikely thing to happen. Actually, you are most of the time left or right, but not that much in the middle. So now the statistics get a little bit screwed up if we think about with mean values. With bimodal distributions, our life changes. And in general, the moment you run a noise process through a nonlinear system, distributions which were pretty become God knows what. You have no idea. And that kind of makes extended Kalman filtering partially complicated. So you have a nonlinear system, you basically linearize it and assume noise gets pushed through in an additive way. In the real system, it's actually pushed through in a nonlinear way and changes the distribution. And you get actually, then when you do estimation, things can go horribly wrong. And then people have all kinds of cool filters. Then you may go to Gaurav Sakatma's classes or wherever you can talk about unscented Kalman filters or particle filters or all kinds of tricks how to avoid these things. This is just a remark. Keep this in mind. This brute force linearization stuff is cute when it works, but it can completely go wrong. And people make careers out of showing that it goes wrong and devising new methods. Okay, that was extended Kalman filtering. You will see in a second how to calculate it, and that this is becoming very similar to LQR control. Good. So in which sense is the Kalman filter optimal? I mentioned it briefly before. We will now go into a notation where we need some hats and some squiggles. So the hat is our current estimate of a state. The squiggle is our next estimate of the state, which is called the prior estimate. Okay, so let me write that down. We will now basically introduce that x squiggle is a prior, and x hat is the final estimate, or we can also call it the posterior. So what does it mean? If I know where I currently am, okay, I'm currently in X, and I apply a motor command U, I can predict that I should be at X squiggle next, but I know that there's a noise process. So this is just a prediction where I am. It's not really correctly what it is. So this is what is called a prior, an a priori belief of where I will be. And then after I basically get a measurement yn, I want to update my prior to get my posterior. That is my final belief. So I predict tomorrow the weather is going to be rainy. Then I get out of my home tomorrow morning and the sun is shining, and then I will update it since it's not rainy. Kind of makes sense. Okay? In the Kalman filter output, what essentially a Kalman filter is going to do is going to look like that. It basically takes your prior belief and updates it based on the error between what you're currently measuring and what you predict to measure, and then makes that your posterior belief. We'll derive that. Well, I'll show you the derivation. It's going to be too long, but it's not so complicated. But this is kind of the famous Kalman update equation, so people know this a lot. The idea is always very simple. Y is basically my measurement equation. So basically, if I plug in my prior, that is x squiggle here, then I get a kind of, if you want, y squiggle n equals t times x squiggle n. That's a prediction what I should be measuring. And I compare it to what I actually measured. Then I have an error term. It's a little bit like PD control. I use basically a gain, like a P gain, and update my prior belief a little bit towards what I should, towards the measurement. And then I get basically my posterior belief. And the trick is now how to compute the K appropriately. Okay. So, having this set up, we can now define some more things. So here's an error, En. And En as an error is simply the true state of the world minus my posterior estimate of the state of the world. Okay? And I can also create a variance of that, which is just essentially square it up and sum it in a one-dimensional case. And what I really try to do is I want to minimize that squared error, or in statistical terms, I want to minimize the error covariance matrix. That's all what I'm doing. So it becomes a least squares problem in the posterior. And you will see that basically the Kalman filter matrix, gain matrix K looks like this. C, you've seen before. R, we know is the covariance. Maybe I should write this down one more time. The expectation of RQ and R, this is I think V. V transpose was R. So that's a covariance matrix. And P is going to be or P squiggle is a prior of the error covariance matrix. That becomes similar to the P we saw in LQR, which was kind of the value function of the system. But this is just summarizing what's going to happen, and I'll try to derive it a little bit. Not too much, but enough so that it's kind of clearer what's happening. K. So optimality is this criterion. That's really what matters. It's a statistical criterion. Cool. These are my favorite slides. I'm not going to go through it. It actually, you will see this is not as complicated as it looks like. It's just because all mush comes at one time. So I'll just write it a little bit, and this will be more reasonable. So fine. We start with what we want to work with. We want to basically express the squared error criterion, which is our error outer product as an n. Okay? This is the criterion I want to optimize. And in the end, what you will see here, all what I'm going to do is I want to take the derivative of this criterion, which is my cost, with respect to the gain matrix K, and basically figure out what is the optimal gain matrix. So the gain matrix becomes my command like in LQR if you want to. So I need something for this. And then after I have this, I can write this. And this is essentially what these two blocks are doing. Cool. So let's do the first part a little bit. So here I get now expectation of, it's not so hard in the end, xn minus x hat n times xn minus x hat n transpose. Okay, so this is the first step. What happens next? So I'm basically replacing x hat with my knowledge of the Kalman filter update equation, how it's going to look like. Remember that was on the previous page, and it says basically that my x hat n equals x squiggle n plus Kalman filter gain times yn minus c times x squiggle n. Okay? This gets replaced by this, just on both sides. Okay? And then I can basically multiply this stuff out. Is that particularly pretty? Well, it depends. Let me see. What do we get there? I need more space, unfortunately. This, and I just write intermediate steps there. So multiplying this out now is done. You can multiply it entirely out. You can multiply it out in more nicer terms. One term which is useful to work with is essentially this xn minus x squiggle n term, and get something which is xn minus x squiggle n transpose. Small remark, the expectation operator of A plus B plus C is expectation of A plus expectation of B, etc. So I can choose it apart, and that's what's happening there. Good. Now, so this is my first term, not very complicated, and we can immediately say, okay, we can define, if you have an expectation operator around this thing, this is going to be my P squiggle n. Okay, we had P. Did they have this ever written somewhere? Was it P? Most likely P hat equals expectation of En transpose. But now I have the squiggle in here. I don't have the hat. So that makes that a prior covariance matrix, and this is a posterior covariance matrix. This is also indexed by n. Okay? So this is basically how we get this term, and it gets later on replaced by P squiggle. Oof, what are all the other terms doing? So then we have a term which basically has the gains in here, basically which is just, again, like a square term, and we have these kind of cross terms. Fine. And now you basically have to see what you can do with those things. Let's see. I'm not sure how much beautiful detail we should go there. We can look at that square term first, okay? And the square term basically has a k here and then has a transpose. You can put the transpose inside, then the k comes over here. And this is essentially what happened in this equation. So you have k transpose k, and then the same term here. The k could be pulled out of the expectation operator because it's not a stochastic term. So fine, next rule of stochastic systems is if you have expectation of a times epsilon, well, only epsilon is a stochastic variable, so a noisy variable, then it's the same as a times expectation of epsilon. Okay? So these are the rules which are applied here. So that gives us this term. And what else do we have here? We have those cross terms where we pull the k out, and we have the cross term where we pull the k out again. And that's essentially all what happened here. So the k just popped out here, this k popped out after the transpose to the right side. Cool. What else happens? Yn minus cx, and I have to check out. So we are having kk here. What is being done here? We basically now replace our yn, which our knowledge about from the model. So this is this guy here. Okay, we plug in that yn is c times xn plus some noise process. Okay, that's all. This y gets replaced here. This y gets replaced here. We have that. What happens over here? Let me see. We do the same thing here. We replace this y here, and replace this y here, which creates a bigger term here and a bigger term there. So fine. If you go through this slowly, you can actually completely reproduce what I'm talking about. Cool. Then what happens next? We have this p squiggle still here. We have k. Then we have c here. And essentially, let me see, cy, okay, we basically pull this v term out as a special term and keep the c terms together and pull it out of those equations. So there's somewhere where the v term comes into being. Let me see, here we go. What is happening? Again, these are all little statistics things. And in essence, I just give you a picture of how this roughly works without going into all the beauty details. So we have cxn plus vn plus cx squiggle n, which is multiplied with the same thing transposed. So cxn plus vn plus cx squiggle n transpose. So this is this bigger term. Fine. I just want to focus on this, the terms which have v and which have x, and multiply things out. So what I'm getting is essentially like c, oops, write properly, cxn plus cx minus k minus okay minus. See, this is why you should never do these things on a whiteboard. Minus here as well, so we get this, and we get this multiplied with cxn minus cx squiggle n transpose. So this was one term. So I basically combined these two with these two. I get another term which is going to be plus, and yeah, it's n v and transpose. And then I get the cross terms, which are going to be vn times cxn minus cx squiggle n, and I get another term. There must be a transpose somewhere. And I get a term from this here plus cxn minus C X squiggle N V N transpose. Does that make sense roughly? Okay. So this is the, and again, I take expectation from all of this, which is really important. Now, this first term, I can now pull the C's out, which is nice. So I can just take C is a constant, it's not changing. On the whiteboard, I can just wipe it out and get here C and here a little bit of space, C transpose plus. And this is what happened exactly here to get this first term. I got the C's out, and I just have xn minus xn squiggle left. The squiggle kind of disappeared here at some point. Okay, then we know that the expectation of Vn transpose is R. That's our definition. This is how we got this term here. The K's there are still on the left and the right side. We cannot ignore them, so it's Kr or K transpose. And then there's those little terms. And those terms are useful. Since Vn is a noise term, it is guaranteed uncorrelated with anything in there. And in general, if you basically have the expectation of uncorrelated terms in general, it becomes 0 in a multiplication. That means these terms here actually disappear to 0. Very happy. And that's what simplifies those equations. So that I have only this term left and this term left. These cross terms went to hell, and I'm very happy. And I only have to look at the next level of terms. I do similar things. I multiply things out. And if there is a V term, and then I get the expectation operator, it kills me. It basically, I can set these terms to 0. Okay. That basically took this bigger equation and made it actually a tiny little bit simpler. And if you now look at this, you get an expectation of this term again, which is my P squiggle again, and I get an expectation of this term again, which is my P squiggle. So I can replace these expectation terms with P squiggle, and I get this very pretty nice equation, which should look familiar in case you remember what we did the last time. Since we now have somehow an equation which says, let me get rid of this entire beauty here. We get an equation which says that P at the next time step, or P that's a posterior, I should say, not next time step, is some P squiggle N plus lots of other things which I know, but everything depends on basically, it's essentially some kind of a function of P squiggle and other constants. And the constants we have are C, currently as we assume K is a constant, R is for us a constant, C, they are all model components. It becomes a little bit like a Riccati equation again, in case you notice that. It's an equation which people understand quite nicely. But now this thing is pretty straightforward. Now we wanted to take the derivative with respect to K and set it to 0 and figure out what is the optimal K. Okay, since this is the cost function we want to optimize, we want to find the gain matrix K, which basically minimizes this covariance matrix. So we take the derivative with respect to K. That means we have to simply take the derivative with respect to K of that term. And K only appears here as quadratic terms and as single terms here. So that becomes very straightforward to take derivatives. Derivative with respect to P goes to 0. So we just have this term left with a K, this term left with a K. Those other terms lose the K entirely. You set it to 0 and you can solve for K, and that is what you get. And that looks identical to what we had as the gain calculation in LQR. So that is the Kalman gain depending on the prior covariance matrix and model parameters. Not too complicated. You can do this. This is not a big deal. It's just, you just have to do it right. You can also do stupid things like multiply everything out and then don't know what to do anymore. And you can do the nice substitutions. We overlook that if you basically have a V term and it multiplies some other stuff in expectation that will go to 0. These are the kind of important tricks there. They're little typical statistical simplification tricks. Good. So that gave us the K part. Let's see, what else do we need? The posterior covariance matrix is thus, now we're going to do, we plug in the K. So we had this already. This was from the previous page, what we wrote down. And now we make it a little bit more handy and try to plug in our knowledge of the K, the Kalman gain matrix. Now this is just now transformation. So here, these two terms have both K's left and right, so you can pull them together. So you don't have so many K's. And then you replace every K with the computation from the previous slide. Okay, this K gets plugged in here. This one, this is 1. The next one, PC, must be plugged in here somewhere. Where is this? Yeah, here. Here's the other. That's K. This is K transpose. And what else do we have? And then we have the case here one more time and there one more time. We have to plug this in. Actually, here I left it in. As you will see, it makes it a little bit better. Now it comes just multiplying everything out. It's not very pretty. And noticing that things cancel. There's two terms. Here's a negative term and there's a positive term. They cancel each other. And what you are left over is something which is much simpler in essence. So just that you can write Pn, or P hat n as I called it here, is the identity matrix minus the Kalman gain. C is our model parameter from our observation equation times P squiggle n. Okay, so that relates our prior knowledge of the covariance with the posterior knowledge of the covariance matrix. Again, I wrote these things out with a lot of detail, so you can actually just look. Every line just modifies a little bit of stuff and plugs things in. So if you really wanted to replicate that, it's not very hard. And last but not least, we need basically the prior covariance at the next time step, since you need to make that prediction for the next time step. And all what it does essentially is you look at the covariance of the error at the next time step, but it's the prior, so E squiggle. E squiggle is going to be at time step n, it's xn minus x squiggle n. You plug that in, again, just inserting the, then you can predict that we now use our model. This model without noise term creates our prediction. With noise term, it's our true information. So what do we have? Here's basically xn plus 1 gets replaced by the true model knowledge. X squiggle n gets replaced by using our knowledge that our prior is basically based on our knowledge of the previous state and the model, but not a noise term. So here's our estimate on the end state, but we want to create the prior at the next state. So that's this here. Okay, and you have it, and you start multiplying all these things out again, and always noticing when a noise term, when you have something like a noise term multiplying expectation of Wn times a constant like R, even that the expectation of Wn is defined to be 0. Okay, this is an R times expectation of Wn, and this is 0 in expectation. So that's how many terms drop out. Again, this is a typical statistical trick. This is the reason why we assume that these variables have mean 0. Otherwise, we couldn't do that. Okay, multiply it out, drop terms, and you basically reduce things to a much simpler form, which here you finally get now the covariance of the system. This is this here. It was just writing this here somewhere, E of W transpose Q, covariance of the system noise, and you get that as a final result. Important, this is not hard to derive. This is very straightforward linear algebra and very straightforward statistical rules of simplifications with expectation operators. Nothing special. Very important, you also notice we did not make any assumptions about the form of a distribution we are using. We only relied on that we have mean zero. That's it. There's other derivations when you go into kind of probabilistic state estimation or whatever, where people make a lot of Gaussian assumptions because they derive it over maximum likelihood or other frameworks. But this derivation is kind of a very pure, simple derivation without any assumption about noise distributions, only mean zero. You can actually push it through and you can show that what you're doing is optimal. Okay, that was painful. The beauty is that's it. That's what comes out of it. I just wanted to show you where it comes from. That's all there is. Again, there's two components. There's the time update equation, the measurement update equation. So from our current knowledge at time step n-1, the previous knowledge, we create our prior estimate of the state. And we can also create from our knowledge at time step n a prior estimate of the covariance matrix. And then you basically plug this in, and you can compute a gain. You can compute the posterior at time step n, and you can create the posterior knowledge of the covariance matrix. And you just iterate through that. And that now becomes really straightforward. It's not a big deal. Okay, we're doing time wise nicely. Some discussions which are useful. So let me clean up a little bit. I don't need any of those things anymore. So some special cases. What happens if you have an extremely noisy system? Okay? That means you would say these model equations here are really lousy. In order to accommodate that misery, I have to create a very big noise term here, so to allow for all that variation which I can otherwise not explain. So the Kalman update equation, so x hat n was x squiggle n plus k times yn minus cx squiggle n. Okay. What they would be doing in this case is essentially they will create a gain which tries to rely as little as possible on your prior estimate. So this is my prior. I predict my prior through those equations, but if I have a huge amount of noise in here, I should not trust this prior. So how can I eliminate that trust component entirely? Well, we can try to figure this out. So we want to basically make this equation not depend on x squiggle at all. So let's figure it out. Plus k times yn minus k c x squiggle n. So this is going to be essentially identity minus k c times x squiggle n plus k times yn. And so can we somehow eliminate this here? So if we can make I minus k c go to 0, we would eliminate our dependence on x squiggle n. So let me see what is the correct result. If we basically, so how would we do that? We can basically simply to make k to be c minus 1. Okay? If that is the case, then I plug in c minus 1 here. C minus 1 times c is identity. Identity minus identity is 0. Okay? And that is basically one way. If you can invert c, you can also invert it in a pseudo-inverse way. How to remove any dependence on your model and completely depend only on your measurements. The alternative, if you totally trust your model and your measurements are total nonsense, well, then you would like to basically eliminate that you depend on this guy. Well, that is easy. You just do k equals 0, so that's 0 matrix. That would completely eliminate that you use measurements and you only believe that what your prior prediction is also going to be good for the criteria. So this is kind of the range what the Kalman filter is going to do. Depending on how you set these noise terms, it will basically push you more towards believing in your measurements or more towards believing in your model equations. Turns out that this becomes a little bit of a tricky parameter system. If you use a Kalman filter ever in reality, let's assume you get this A, B, and C stuff relatively straightforward. But these noise components, how would you get to them? Well, this here is measurement noise. So measurement noise you could, for instance, do by simply having your robot system running, and you basically put it in a steady state, and measure the same state again and again and again and again, and then basically compute the covariance matrix of it, or the variance, whatever it is, multidimensional or not. Okay? So that would literally be what I showed you before. You take the sum of measurements like yi and do I equals 1 till n, assuming you get n measurements, so 1 over n. So this is going to be your y. No, it's not hat. It's going to be your mean, and then you do compute yi minus the mean squared 1 over n. And this is going to be your variance, which in our will would become your R. Okay? So this is using the physical process to measure things. Now, it's a simple way of doing it, but should normally do the job. Now, getting the noise on your process is harder, because you don't really know what to put there. This is where you start playing, essentially, with the Q parameter. You scale it up a little bit, you scale it down a little bit, and you see until your filter finally performs well. Sometimes you get actually also sort of noise processes where the measured variance is really small. But if you make the measured variance really small, then the numerics of your Kalman update equation become a little bit more unstable. So often people inflate it a little bit and be more negative about it. So it's annoyingly, it turns out that these two terms, this one you can physically constrain a little bit. This one is a guessing term, and you play with them until you get the performance you want. Now, if these are matrices, which we care about, the covariance matrices, you also have a whole bunch of parameters on the diagonals to play with, so you have to be careful with that. So it takes a little bit of work to figure it out. You also have to now, if these different states mean different things, like some are position, some are velocity, they have different units. So this is not just going to be a unit, an identity matrix multiplied with a scalar. It may have all kinds of terms in there, which you have to adjust appropriately. So that's the twiddling part, which is annoying. Okay, we just quickly talked about this. And so what then Kalman filtering is doing essentially is, so this is just from a textbook. This is about some voltage measurement on the number of iterations. You get very noisy data points, and this is your posterior estimate, and it just converges usually nicely to the true estimate over time. So this is very trivial. But it's what you usually see. So you get a very noisy system, but over time it quickly focuses down and you get a reasonably denoised estimate. It's not going to be clean. It's still going to wiggle around a little bit, but it's going to wiggle around much less than the data is going to wiggle around. And you can also look, so what is the error going to look like? The squared error, basically, it nicely drops over time, and you're basically getting where you want it. This is what we plan to do. Remember, we try to optimize the squared error relative to the true value, and that should hopefully go down and converge after some time. It will never become zero. If you have a noise process, you can never expect that you get the perfect value out of it, but you can hopefully get very close to a decent value. Okay, that was it. That was Kalman filtering. Important message: Kalman filtering for linear system is very similar to optimal control. It's derived from a similar optimality concept, just based on statistics. Actually, one thing which is interesting to note is that when you have linear systems, you can do Kalman filtering independent from deriving an optimal control law. The two of them do not interact, which is kind of cool. It's called the separation principle. In nonlinear systems, this is not true. And everything can become very complicated. So basically, if you do state estimation with filtering, it will actually affect what you can control afterwards in a strange way. And you get interaction between both processes, and things can go arbitrarily wrong. So people are very unhappy about this in nonlinear systems. But in linear systems, it's great. Filtering and control are two separate topics. They simply separate automatically. Just nice to know. All right. Try this simulator. Please give me feedback that it works or doesn't work, since your homework will come very shortly and you will need to install it somewhere. Thank you.